directly gone into presentation mode somehow. Okay.
Good afternoon, all. To all. As a member of Bearing Sectional Committee PGD 13 of BAS, it's a privilege for me to today present presentation on Aero Gasturbine bearings. And I thank BAS for giving me an opportunity for that. Per se, HAL does not design bearing or manufacturing bearing, but as a journey like development of a gas turbine engine or manufacturing process technology transfer, bearing usage of bearing is a journey like any other component. So HAL has acquired, and as a designer, whatever the knowledge I acquired, I want to give a glimpse on that. I don't want to go to the kinematics because you people, basically the manufacturer or people have done research on that, they can give better idea on kinematics. So I want to just know how bearings are selected and how they fit into the gas turbine. That aspects I want to cover. So my presentation covers introduction, then selection, design of bearings, and then special requirements pertaining to the gas turbine engines, aero gas turbine engines, then bearing materials, lubrication, testing, inspection, storage, then defect investigation, failure modes, and standards. So as we all know, rolling element bearings are the key elements of high-speed aero gas turbine engines. Because of that, a lot of innovation is happening. So for the ever-growing demand for reduction in weight, performance, vibration, noise, power loss, and to increase the speed, reliability, and life. So broadly, bearings in aero gas turbines can be classified into mainline bearings, which support the LP and HP rotor bearing systems, and there are gearbox bearings, then accessories bearings. My presentation covers most of the time on mainline bearings. For the mainline bearings, the selection and or design of bearings or right bearings is very important from the point of selecting a proper bearing arrangement for the smooth operation of the aero gas turbine engine. And also, we all know that in aero gas turbine engines, bearings have to operate in a very harsh environment of very high temperature, and for the better aerodynamic performance, they have to operate at a very high speed. And dimensions of the aero gas turbine mainline bearings are decided by rotor dynamics or the envelope limitation of the engine as well as the shaft strength. So therefore, for the selection and design of bearings, these are the factors which influence rotor dynamics of the rotor bearing system, then high speed operation for improved performance of the, and as well as reduced weight, then various loads such as aerodynamics, maneuvering, inertia, unbalance, etc. High temperature from the external environment as well as the internal friction, then the lubrication system as well as the lubricant type used, and the right material to be used to have an optimum and longer utilization in line with the engine TBO. So we take bearing as a whole system of rotor bearing system. So these are the main challenges of selection as well as design of mainline bearing. Like in aero gas turbine engine, the mainline bearings have to undergo combined thrust, radial, and moment loading, supported in flexible mounts, leading to non-uniform variation in deflections, contact stresses, and fatigue endurances. As well as the rolling elements have to undergo high inertia forces as well as gyroscopic moments, as rolling element surfaces are subjected to alternating stresses at a high frequency as well as subjected to high centrifugal forces at high speeds. And also, most of the aero gas turbine engines, they have to undergo high level of maneuvering, so that additional load also comes from the bearing. And also they have to operate at high speed at high elevated temperatures. So based on these factors, the selection of and or design of bearings will be categorized into two types, like based on the factors based on rotor dynamics and other design aspects such as loads, alignment, mounting, temperature, etc. We have to decide how many number of bearings are required to support a main line shaft, and what type of bearings you have to select. Then what type of bearing arrangement or fitment is required on the shaft as well as housing. Then what type of bearing housing or support is required, whether it should be a flexible housing or a rigid housing. These are the four commonly used, like there may be some exceptions, but these are the four commonly used bearings in aero gas turbine engines: deep groove ball bearing, angular contact bearing, and 3 or 4 point contact bearing, which have to confirm like precision class ABS 7 or ISO 4, then cylindrical roller bearing. So this is actually a special requirement of aero gas turbine engine, where to suit into the rotordynamic requirement, a flexible cage, that is commonly referred as a squirrel cage or centering spring. Also, sometimes we have to incorporate a squeeze film damper to attenuate the excessive vibrations at critical when it is passing to the critical speed. And sometimes the bearing manufacturers integrate this squirrel cage along with the outer race. I just want to show you some of the arrangements. This is our legacy design PTA 7. This is the first certified engine in India by HAL. It's successfully certified and used for Lakshya aircraft. And it has got a lot of potential. Recently, we have found that it can be used in many unmanned aerial applications. Initially, it was designed for 5 sorties, maximum 5 to 10 hours. Then it was extended for 10 sorties, sea dunking. Then total life was something around 20 to 30 hours. Now we are aiming at 200 to 400 hours life. So it has got it is a simple rotor bearing system. It has got 2 bearings, bearing 1, which is a 3-point ball bearing, and second one is a cylindrical roller bearing. The arrangement I have shown: bearing 1, angular contact 3-point ball bearing, bearing 2 is a cylindrical roller bearing. So both bearings have got squirrel cage, but doesn't have a squeeze film damper because we are using a mist lubrication. So it is not possible to provide this squeeze film damper. So also we have got other class of engine, the type 2, based on GTS. We have developed GTE G60, which has replaced the GPU of AN32 aircraft. It is a simple arrangement. Left is a deep groove ball bearing and right is a cylindrical roller bearing, and it too has got squirrel cage. And third type is it's a Shakti engine, which is powering ALH, like a class of helicopters. It has got one gas generator spool, another one is a power turbine spool. So supported gas generator supported on 2 bearings, and power turbine is supported 3 bearings. Fourth type is it is a 2 spool coupled with the intershaft bearing, where it is driven by both HP as well as LP. So fifth type is it's a big class engine, where intershaft bearing is generally a roller bearing. Yeah. Yeah. Okay. This one, sir. This is the Shakti engine. So similar, we are developing a similar engine called STSC engine indigenously. The development is going on. It's more or less, this is 1000 kilowatt engine, whereas the ST is a 1200 kilowatt engine. Where gas generator spools. Next one is this one. large engines. Okay. So, and the second type of selection is based on their temperature environment, as well as rolling element surface are subject to alternating stresses with high centrifugal forces resulting into limited fatigue life. So we are using a tool for our reference limiting factors DN. Say we are very close to 2 million. So there was a discussion yesterday that maybe but whereas our bearing designers, they were telling that even they can go beyond 2 million also, maybe up to 2.5, and also FN. Based on this, we are selecting the bearing materials and lubrication systems and lubricants. Bearing materials are, these are all the general references, materials are selected based on their high fatigue strength, high hardness, capability, then high wear resistance, shock resistance, heat resistance. For some some requirement, there may be a shock resistance is required, which are subjected to high shock loads. Then heat resistance. Then some applications very good corrosion resistance is required. Then high mechanical strength and high dimensional stability. These are the type of materials. Some used by us, like in engine division, as well as some are given by our bearing designers, which we are not using currently. First is a tool steel, which are through hardened, like ASI 52110, it's 100 CR6. That's very extensively used in our technology transfer engines, which are designed from 1950 to 1970, 80s. Almost all engines are using that material. Then later on, they have started using Z100 CD17, that is 440C. So then we have for our corrosion resistance environment, we have used BG42. Then we upgraded to Chromex 40. In a case study, I am going to explain that how you change it. Then now after 1980s, M50 is most commonly used in aero engine industry. Also M50 nil also. Then ceramic material is now started since last 15 to 20 years. A lot of application has come. So same explanation I have given. Chromex bearing. Chromex bearing, actually it was developed by SNFA, and we also used in our application legacy design. Then there are some new materials like Chronadier, also referred as Nitromax, VC440T, 444. They are all used. They are being used presently, and they are replacing 52100, M50, 440C, BG42, and Chromex 40 materials. And in some applications, they told that some of the rings can be made using Inconel 718 material also. And ceramic nowadays is commonly used for high-speed ball bearings for their higher wear resistance. And we have used way back in 2000 itself, we replaced BG42 balls into ceramic, and they are working fine. Ceramic ball has got advantage, material has got, it is 42% inertia force exerted by ceramic force ball is 42% lesser than steel ball, but it can be disadvantage because of the modulus difference. They can induce very high contact stresses, so it has to be designed properly so that the contact stresses are within the limit. And bearing materials for cages. These are some of the bearing cage materials used in our engine division technology transfer programs, as well as for our development we use. So, and based on this, like a selection of bearing material at times can be iterative, depending on the internal external operating conditions of the aero engine. So as I told, we take bearing as a system. So that a lubrication system is very important for the longevity of like proper functioning, smooth functioning of rotor bearing system. So there are like these are the types of lubrication we use it actually: grease lubrication for some of the accessories and air oil mist. PTA 7 uses oil air mist lubrication. Then some requirement there is a oil bath lubrication also. Then closed loop circulation system using a pump driven by the engine itself as well as driven independently. So this is the like oil system. So total system, like it itself is a complex. We have got a system oil system engineers who work on improving the oil system for proper lubrication. The circuits. So based on all these things, design of bearing in a gas turbine aero engine for specified requirements such as load carrying capacity, speed, temperature gradients, misalignment, minimum drive required, preferred material and lubricant system can be like this: estimation of displacement and contact. This is all shared by our bearing design manufacturer. What steps some of the things they share with us. Based on that, I've listed estimation of displacement, contact stresses, then bearing geometry definition involving stress and life calculations, then diameter clearance variation, calculation of interface contact stresses, hoop stresses, minimum fit or fits to be used. Then a free state bearing geometry comprising of free and operating internal clearances, cage selection, cage section with clearances, pocket clearance, etc. While like from our point of view, we want to look into critically these following things, like minimum, and that's what we always give stress on these things, minimum and maximum loads on the bearings which have to be considered. Then bearing mounting with preloading and stiffness and clearance details, lubrication with viscosity, degree of contamination, shielding, etc. Then steady state and occasional transient overspeed, because most of the time our engines will be like overspeeding above 100% speed. That has to also be considered. Then operating flight cycles. So this is like the calculation of life, like as ISO 281 and IS 23821 life, like L10 life is given like this. So whereas now we use like some of the factors try to have a better life factors. Then coming to testing, after we design, manufacturing, everything, that bearing has to perform to its what for it is designed. So testing is very important. Like there are testing methods for performance and endurance testing on test ring, then performance and endurance testing on engine, and in-service testing. We collect a lot of data, and based on data we estimate the performance of the bearing. Performance testing of bearing is carried out for the following requirements. Like we collect a lot of data such as bearing temperature variations, frictional torque characterization, estimation measurement of oil consumption, and variations in bearing dimensions. Then in endurance testing, we try to collect bearing temperature variations, oil consumption, then vibration patterns, variation in bearing dimensions. At the end, whatever the bearing is designed, it has to perform inside the engine. It has to undergo the required like endurances, and it has to be proven in the inside the engine. So the in a prototype engine, we carry out performance evaluation and initial flight required for initial flight clearance of 150 hours as well as engine TBO. And these are the parameters we evaluate: bearing temperature variation versus operating speeds, vibration patterns, oil consumption, oil analysis, and oil temperature measurement. Then variations in the bearing dimensions between each interval of testing. So this is the typical, we do a lot of measurement, but I have taken only the minimum data we take. Like we take JPT, because bearing temperature, especially RBT, the bearing which is in the hot zone, which will be influenced by the hot gases. So JPT, front bearing temperature, rear bearing temperature, then oil tank temperature, because that is also important. Then vibration. So these are very important, which are always will be monitored, whether it's a production engine or development engine. In the development engine, we do a lot of other measurements. So bearing condition monitoring through vibration measurement. So these are the basics of rotational frequency, ball pass frequency of outer race as well as inner race, then fundamental cage frequencies, then 2 times the ball spin. These are important to evaluate in a defect investigation. So we always know, like, diligently take the vibration measurement and try to evaluate. Then another aspect is inspection and storage. Like we actually, since our collaboration with a lot of foreign country like engines, so they are having a lot of standards. So we try to implement in our design also. So there are the AR standards, there is other standards. So we do maintenance, evaluation, everything. So we have procedures based on our collaboration for each bearing. Intermittent inspection procedures are there. There are task directives, so we check it even after use or a shelf life. In between the shelf life, we try to evaluate. We have got a bearing hospital inside engine division, which it caters to many organizations. So we have got a very systematic procedures laid down. Then defect estimation is very important part of our like any other component. Bearing also, if any failure happens or any problem we encounter, we do a thorough investigation. Like we will have a DI committee. So in the we have got a lay down procedure. Like we have to have comprehensive history of bearing, build details, how many, all this information we have to have. Then if required, we will have a comprehensive examination, which will include bearing manufacturing date, shelf life details, bearing as an assembly, individual elements, detailed examination under magnified and microscope, and also lubricating oil detailed examination will be carried out. Then the mating shaft as well as bearing support detailed examination will be carried out. So based on our experience, these are all the types of bearing failures, and we find that fatigue failure is always less than 10%, whereas most of the failure in a development as well production engine, the failures more than 90% time the failures are due to overheating, lack of lubrication or oil starvation, mishandling, misalignment, improper mounting, trapped hard particles, corrosion, etc. I will show one case study on this. Actually, we had an issue like initially for this particular bearing arrangement. It's way back in 1980s. That time we designed that engine as a design. So it has got 2 bearings. So it was supposed to work in a very corrosive environment. So at that time, only 2 material selection options were there. One is 440C, another one is BG42. So based on the advantages of BG42 material was selected. So because in BG42, vanadium with chromium content enhances the corrosion resistance. Chromium, molybdenum and vanadium together make up approximately 20% content in the material. Also, it enhances the wear resistance. But unfortunately, both bearings failed before completing the intended service life.
Excuse me, 5 more minutes.
Yeah. So investigation, investigation was carried out, and it was found that the corrosion pits distributed all at random over the race face circumference, rib faces, cage, guiding bore diameter, the faces and fillet radius of both outer and inner rigs, as well as presence of numerous corrosion pits and thin scratches all over the rolling elements. These are the pictures. So for that, actually, the time I joined, actually, it happened from 1998 to 2000. So that time I just joined HAL. So this was the issue. So one of the bearing, it was sent to SNFA, who actually designed and manufacturing the bearing, and they found that corrosion pits are the corrosion is the reason for this failure, and they suggested alternate material. That time they came up with the material called Chromex 40, they gave the justification used. So we used the bearing, and they gave the technical details also. What is the difference of hull stress when used when we replace with the Chromex 40 material, and also they gave the design data. Earlier PG42 we compared with Chromex 40. And we found, we accepted under their justification, we went ahead with Chromex 40, and after using Chromex 40, rings and rolling elements, the bearings cleared 100% intended life, and it's successfully used. So finally, since we are using ISO standard as well as IS standards. We use a lot of American because of the joint features like technology transfer. We are having because most of the foreign manufacturers, they give technical directives to use either their standards or European or American standards, as well as material standards and lubrication standards. So, thank you, sir.
Thank you, Dr. Gonzalez, for your deep insight into the selection of Gasturbine bearings. Now, time for questions.
Presently, we are planning to operate the aero engine something around 1500 degrees centigrade. So, but what is the maximum temperature the main shaft bearings come across?
Actually, since we supply lubrication, no? So temperature, actually we measure the temperature, like we don't allow the bearing temperature go beyond 270 degrees centigrade. We measure, actually in every engine we measure the bearing temperature at the outer race. So that is the criteria, so we don't allow.
Yeah, but that is what is my question actually. If the operating temperature is 1500 degrees centigrade, how the bearing temperature will be constrained to 270 or 300?
Like cavity design, that's why, you know, like it's a system. So we have got a oil system people, there's a cavity design, labyrinth seal design. So bearing will not be operating under that kind of high temperature, though it is close to that hot temp. So that's why I just give an introduction, because that itself is a big failed. So bearings will not be subject to that kind of a level of temperature.
Yes, sir. One question from my side.
Yes.
You just shown us the modified way of calculating dynamic load rating for a bearing in comparison to ISO 281 that prescribes a general way of equations for calculating the dynamic load ratings.
This is only just, you know, like what they share, like
okay. That's
why we are also trying to implement. We generally follow ISO only.
Okay, sir.
But that material factor, loading factor, lubrication factor, and all, no, it will give. We are trying that.
Okay.
That's just I presented.
Right, sir.
Related to the operating situations, are these bearings are being monitored by a conditioning monitoring?
Yeah, so that's what I shown. No?
Yeah.
Every minimum condition monitoring I have represented: bearing temperature, JPT, oil temperature,
Yeah.
vibration. Continuous it is monitored. But many development engines we have more like now telemetry is there.
Yeah.
We are trying to monitor a lot of other parameters.
This sensorization, whatever you are saying, is this been inbuilt done by HAL or how?
That's it.
Okay, thank you.
Yeah, we will have more questions in Q&A session. Now it is the time for next presentation. Thank you.